Hello everyone, my name is Yonghao. In this video, I will introduce our recent work about remote sensing image generation from text using modern Hopfield networks, which was conducted together with Weikang, Padron, Michael, and Sepp. I will start with some background knowledge about text-to-image generation in both computer vision and remote sensing fields. Text-to-image generation is actually an interesting task which aims to synthesize realistic images based on the given text descriptions. And in the early study of this research direction, researchers mainly focus on the GAN-based method. And the first pioneer work is the text conditional GAN. The idea of this work is very straightforward, that we have a GAN model and we use a generator to synthesize realistic images based on the given text features and aims to cheat the discriminator, while the discriminator on the other hand aims to distinguish whether the input image is real or fake. And to generate images with higher resolution, researchers have also considered to add constraint with some key point locations. And here you can see the generator here will not only receive the text descriptions, but also receive the key point locations with this coordinates information. And with this technique, this method can generate images with 128 by 128 pixels. Another well-known work is StackGAN, and the idea is to generate the image with two stages. So in the first stage, the generator will have a kind of a blurry output, and you can see this result is not very good. And this blurry result will be regarded as new inputs and be fed into the generator in the second stage to synthesize higher resolution images. And these are the results from different stages. Apart from this aforementioned GAN-based method, recent research focuses on the transformer-based method, and one of the most representative works is DALL-E, which was proposed by the OpenAI. So this model contains 12 billion parameters, and the authors in DALL-E also collected 250 million text image pairs to train this relatively giant model. And these are some demos of the generation. And you can see, for example, the text here is an illustration of a baby daikon radish in a tutu walking a dog. And it's actually very interesting that DALL-E can well generate the images based on these descriptions. And you can see this generation is also in a kind of a cartoon style, which is very cute. And very recently, the DALL-E 2 has also been proposed. So here is the flowchart of this model. So you can see above the dotted line, the authors are trying to train a text image matching model using the clip objective. And once the training is finished, under the dotted line, given a text descriptions, the authors will first get the corresponding text embeddings using the pre-training model, and feed this text embedding to a diffusion prior or the autoregressive prior to get a corresponding image embedding. And finally, this image embedding is fed to a diffusion decoder to finish the image generation. And we can find that compared to DALL-E 1, the image quality of DALL-E 2 is much better, and the spatial resolution can reach 1024 by 1024 pixels. And another interesting work is imaging from the Google Brain, which is also based on the based on the diffusion model. And you can see the generation quality is really high here. Okay, so far most of the research focuses on the image generation of natural images, while the related works on the remote sensing scenario are still very few. And here is one related work about structured GAN published in 2021. And you can see that the generation results are still not satisfactory. So the main goal of our study here is trying to propose the first descent text-to-image generation work in the remote sensing scenario. And you may also know that compared to the computer vision task, remote sensing tasks generally put higher requirement for the realism of the generated images. So we aim to synthesize those realistic images. For example, here are some demos from the generation result of our method. Now let's see the proposed method. This is a flow chart of our method. Similar to the DALL-E 1, we first use the byte pair encoding to get the text tokens and use the image encoder to transform the image into the image tokens. And for both text tokens and image tokens, we will transform them into the embedding and concatenate them together. And then we will feed this text image embedding into the proposed prototype learning block, which consists of one Hopfield layer and a self-attention layer, then followed by another Hopfield layer and softmax function to conduct the auto-regression. And in the testing phase, once we get the predicted image tokens, we can feed these tokens into an image decoder to conduct the image generation. Specifically, we will first train a VQAE model. And the main component in the VQAE consists three parts. That is image encoder, image decoder, and a codebook. For this codebook, we have K code words, and each code word is a D-dimensional vector. And given the input image, we first use the encoder network to tokenize it and get the encoded features. And these encoded features can be further transformed into the indices, where each index is actually can be regarded as a prediction that's the nearest code word for each pixel in the feature map. And based on this codebook index, we can obtain the corresponding image embedding by simply copying the corresponding code word from the codebook. And once we get this image embedding, we can use the decoder network to obtain the reconstruction image X prime. And finally, the whole network is optimized with the constraint of this reconstruction loss, which is implemented with the mean squared error. And once the training of the VQAE is finished, we will fix the parameter weights in the encoder, decoder, and the codebook. Now let's see the proposed prototype learning block. As we mentioned before, each prototype learning block consists of one Hopfield layer and one self-attention layer. Both are inspired by the work here. The Hopfield network is all you need. So you can see from this figure that how this Hopfield layer looks like. Each Hopfield layer actually contains two key matrices, including a prototype lookup matrix, W lookup, and the prototype content matrix, W content. And with this equation, we can achieve the prototype learning through the Hopfield layer from two different perspectives. And the first one is learning the most representative prototypes and saving the stored patterns in the prototype content matrix, W content. And the second one is learning to represent the input text image embedding features with the learned prototypes using the prototype lookup matrix, W lookup. And then we will further use the self-attention layer to strengthen the inner information interaction among different tokens in the input text image embedding feature X. And this is an illustration for this self-attention layer. I think most of people are very familiar to self-attention. And key components here are one query transformation matrix WQ, and another is a key transformation matrix WK. Okay, and after these prototype learning blocks, we have another Hopfield layer. And the main difference of this Hopfield layer is that the dimension of the prototype content matrix is changed to the n prototype by k, where this k parameter indicates the number of code words defined in the VQAE, so that later we can regard the output feature z as the predicted logis. And here let pi denote the predicted logis of the i's image token, and let yi be the one hot form of the i's input image token. Then we can define the cross entropy loss, LCE. So the whole network is optimized with the constraint of this cross entropy loss. Once the training is finished, in the testing phase, if we get the predicted image tokens, we can then feed these tokens into a decoder network which was pre-trained in the VQAE, and then we can get the generated image. Now let's see the experiments. In this study, we used the RSICD dataset, which was originally collected for the image captioning task in the remote sensing field. It contains 1,921 remote sensing images with a spatial resolution of 224 by 224 pixels. And here are some demo images and corresponding text descriptions. And following the previous works, we used those 8,734 images from the training set to train our model and test the performance on those 2,187 images from the test set. For the evaluation metrics, we adopt the inception score, FID score, and additionally, we propose to use the zero-shot classification and use the oral accuracy as another metric. And the main reason here is that for metrics like inception score and FID are originally proposed to evaluate the performance of the GAN model, which may not be accurate enough to measure the semantic consistency between the generated images and the original samples, so that we come up with the idea to train a classification model, for example, the ResNet 18, based on the generated images using the text descriptions on the test set. And then we conduct the zero-shot classification on all images in the original test set. And we use the oral accuracy in the classification as another metric to measure whether the generation quality and the semantic consistency of the model. And here are some of the comparative methods used in this study. And so this Txt2Img-MHN represents our method. And we also consider to replace the VQAE by the VQGAN to analyze how different image encoder and decoder will influence the performance. So we first visualize the image reconstruction performance using VQAE and VQGAN. So here we can see, compared to VQAE, VQGAN is more powerful to preserve the detailed spatial information, and the result of VQAE is somehow looks very blurry. However, there's also a risk for VQGAN that the shape information of the original ground objects may be changed. For example, in the second column, we have many storage tanks, these wide storage tanks with a round, with a kind of circle shape, which can be well preserved in the VQAE, but may be changed to like rectangular ones in the VQGAN. Okay, These are the generation results of different methods given this image, given these text descriptions. You can see that although the existing methods like dfgan and lafit, they can generate images with very similar visual appearance style compared to the real images. They can clearly preserve the accurate shape of the ground objects. For example, the playground here, and also this kind of stadium. So for this method, the result may be inaccurate. By contrast, the proposed text-to-image modern Hopfield network can yield much accurate in these scenarios. And one characteristic of the proposed method is the diversity of the generated images. We compare our method with the dfgan and the lafit, and we generate the images 9 times using the same text descriptions. You can find that for lafit, the images basically are identical among different repetitions, while the proposed text-to-image modern Hopfield network can possess higher diversity and at the same time will preserve the semantic consistency of the image to the text descriptions. And this is another example about the viaduct. Okay, here are the quantitative results on different methods. As we mentioned before, that we have the results for inception score, FID score, and zero-shot classification OA. And it's actually very interesting to see that for all GAN-based methods, they can achieve much better results on the metrics of inception score and FID score compared to the transformer-based method. However, it should also be noted that the method achieves the best performance on the inception score may not achieve very good performance on the FID score. By contrast, we argue that the zero-shot classification OA may serve as a better metric to evaluate the performance of generation results, especially from the perspective of the semantic consistency. And we can see that the proposed text-to-image modern Hopfield network can achieve the highest OA of 65%, which outperforms the other methods with a large margin. We also conduct some parameter analysis about the hyperparameter number prototypes. And you can see if we set the prototype to a relatively small value, for example 10, this will restrict the performance of the proposed method. So to balance the performance and the computation burden, we fix this parameter to 1000 in the experiment. And to further understand what the Hopfield layer have learned in the experiments, we further visualize the top 20 tokens learned by the last Hopfield layer. And it's very interesting to find that actually these top 20 tokens corresponds to those fundamental components to generate an image, like different colors and the different textures. And some of these tokens may share many similarities to specific ground objects like meadows and desert. Finally, I will make a brief summary for this talk. So in this study, we propose a text-to-image modern Hopfield network to synthesize realistic remote sensing images. We further comprehensively compare and analyze the performance of VQVAE and VQGAN for text-to-image generation in a remote sensing scenario. We also find that the overall accuracy in the zero-shot classification may serve as a better criterion for the text-to-image generation task, especially from the perspective of semantic consistency. We have also made a Maker project page in the GitHub, and if you have interest, you can scan this QR code for more information about the code and the pre-trained models. Okay, that's all for this talk. Thank you for your attention.